Hello, today we will be discussing the power of a cyclist. So the purpose of this lab is to model the acceleration of a bicycle and explain how this corresponds to the amount of energy expended by the cyclist. And from the values determined through the Python program and the physics calculations, we were able to determine the average power of the cyclist. When compared to professional cyclists that use computers to calculate this power, our value is very reasonable. So our lab and models are a success. To outline my lab, I will discuss the physics content models necessary for analysis. I will then discuss or show the tracker video and Python program. I'll then discuss the initializations, the calculations, and then also the result. So the models used in this lab are most evidently the momentum principle, because we go from the motion of an object to determine the net force and acceleration. And then also we are concerned with the angular acceleration, because we move from the tangential acceleration to the angular acceleration, which is useful later. And then also we are concerned with the torque, where torque is the moment of inertia times the angular acceleration. And this is useful for determining the amount of torque on the back tire and also the amount of torque of the force on the crank arm. So in the Python program, we wanted to move from the position data to a net force and acceleration. So I used the same program that we used in Lab 3. And I kept pretty much everything the same, except I changed parameters such as only using the x direction. And then from this we can compute the tangential acceleration. Now here we can see the video file being run in Tracker. And we can see over on the right hand side that there is a slight change in the slope. So there is a change in the velocity. It's very little, but it is present. And from this change we can get the acceleration, which is then useful in calculating the net force. So here's the Python program that I used, and I will go ahead and run this. It was a fairly simple model where I have the yellow ball as the origin and the blue ball as the motion of the cyclist moving towards the left. And I also asked for the Python program to print out the change in velocity over the change in time, which is this vector here, which was important because this is the acceleration. It's the tangential acceleration, which I can then use later in the lab. So first of all, we need to consider a few initializations in this lab. First, that the friction force of the ground is negligible. And also I'll explain a couple of these. The cog is the gear in the rear wheel. The chainring is the large gear next to the cyclist's feet. The force, the F, that is actually what we're trying to find. P is the length of the pedal crank arm. And then also F2 is the force on the ground by the wheel, and then also the tangential acceleration, which is what we were finding in the Python program. So here's the core of the lab where we have done our calculations. So we know that Fnet always equals ma, and we calculated the tangential acceleration through the Python program. So compare this to the angular acceleration, and then we wind up with a term which is Fnet equals the mass times the angular acceleration times the radius of the wheel. And we also know that the torque is equal to the moment of inertia times the angular acceleration. So when we compare the net torque, which is going to be the force of the cyclist's foot times the length of the crank arm times the ratio between the two gears, and then minus the force of the wheel times the radius of the wheel, this is going to equal the moment of inertia times the angular acceleration. Now we do some mathematical calculations, then we wind up with this bottom term here, which is equal to the tangential acceleration. And we found this in our Python program. So now we have a bunch of terms with knowns, and the only thing unknown is the force applied by the cyclist's foot. So we carry that calculation out, and we determine that the force applied by a cyclist's foot is 198.03 newtons. So the final results of the experiment. So the number of rotations of the crank we had was 2, which we could see in the tracker video. And this is equivalent to 4 pi r, which is approximately 2.4 meters. So this means that the force of the cyclist's foot acted through a distance of 2.4 meters. Let's compute this into work, and we see that this was about 472.88 joules. Now, we want to compute this also into watts, so we divide by the total amount of time that we observed, and we compute that we have 430.3 watts. Now, to see how this compares to actual computers which are placed on bikes, we looked up a Tour de France cyclist will average approximately 380 watts over an hour-long time trial. So, given that I was only acting in approximately 1 second, it is very reasonable to assume that I expended approximately 430 watts. So to conclude this experiment, our computational model and observed data actually worked hand in hand to give us valuable information such as the tangential acceleration and the force supplied by the rear wheel. And the data does fit the model in the sense that our results were very similar and reasonable to actual results determined by computers for professional cyclists.